Good day, students. We're continuing along on our discussion of waves and in particular sound, which is what we'll be focusing on more in the next chapter. The place where we left off the other day was on transverse waves. We did mention that transverse waves act like disturbances of rope or the disturbances of the surface of water when you throw pebbles into it. Those are all ways or which we make transverse waves. Now today we're going to focus more on longitudinal waves because longitudinal waves are really the direct analogy or I would say the direct content of sound waves. So let's review that shortly or go over it. We had an example of a slinky, and I'll repeat that one here again. We attach one end of the slinky to the wall, and we have some tension on it so that it doesn't sag, and we apply a jerking motion in and out, back and forth towards the wall and away from the wall, and there will be some frequency associated with that because my hand takes a certain time to go in and come back out. We call that one full period of the oscillation, which in this case is my hand generating waves on the slinky, and that is called the period. And the inverse of the period is the frequency. So I'm applying a certain frequency with my hand motions back and forth, as you can see here. And what occurs is that as we push in, we make a compression of the slinky, and as I pull out, we make the opposite of compression, which we call rarefication, which is a stretching of the loops in the slinky. And as we continue with this process, what happens is that the initial compression that was made starts getting transmitted down the line and heading towards the wall. Now eventually that compression will reach the wall and get reflected back, but before it does so, you can see that it's traveling along, and after the rarefication, which is the jerking of the backwards, I have now finished that rarefication or opposite of compression of the stretching of the slinky, and I now have two compressions that have been created after I push in again, of course. And I've got the first compression that started at the bottom of the page, and then the second compression that starts at the top of the page. And in between, I have what's called the rarefication. And this sequence of compression, rarefication, and compression is what generates the wave property of the slinky, and furthermore it is a longitudinal wave because the oscillations occur along the direction of travel of the wave. It's longitudinal with the velocity of the wave, which is in this case heading towards the wall. So the compressed part is formed by pushing towards the wall. The stretched part is formed by pulling from the wall. Repeating the push and pull sequence once per second will make a longitudinal wave with a frequency of 1 hertz. And the molecules of the slinky only travel a very little from their static positions. It's the compressions that travel at the speed of the wave. So that's the basic idea, and the reason we emphasize this is because it is directly most similar to sound waves, which are also compressions and rarefications of the air molecules. And we'll see that in the next slide. So imagine that, for example, we have a tuning fork, and the tuning fork is dinged with your hand or against a piece of wood. It begins vibrating, and the vibrations of this tuning fork will typically be or can be in the frequency range that your ear can receive. Now remember, we said that the ear can detect sound vibrations as low as 10s or 20 hertz and as high as 20,000 hertz. So the tuning fork is going to have some value in there. If it's the type we can hear, it could be, for example, 400 hertz as an example. But what happens is that as the fork begins to oscillate away from equilibrium and pushing towards the long tube that will direct the sound wave, then the compressions of the air molecules are formed when the right side of this fork begins to push the air molecules further to the right, and it will compress them, and that gives you the compressed air molecules that you see in the tube. Furthermore, when the oscillation of the tuning fork is in the opposite direction, away from the column of air, then it will create a rarefication of the molecules, and then when the next time it goes in the direction of the tube, it will create another compression. So we get compression, rarefication, compression, rarefication, compression, and this whole train of compressions is moving down the line, even though the molecules themselves move very little from their equilibrium position. Okay, so this one basically just shows us that how to calculate the frequency or the period from the frequency. I'm going to skip over this. I think it's not terribly important for us at this point. I think you all know how to do that. But this one is probably more important, and that is that it states that the wavelength of the longitudinal wave is the distance between A, successive compressions, B, successive rarefications, both A and B, or none of the above. So in this case, if we go backwards, if we go back and look at the example that we had, what we see is that we can think of the compressions as being a region of high pressure, high density. And so if I were to plot density of air molecules along here, it would go high density, low density, high density, low density, and that produces a sine wave. So the distance between the high density regions would be equal to one wavelength, and similarly the distance between low pressure or low density regions of the air molecules would also give us one wavelength. So in this case, what we see is that either one of either the compressions or the rarefications that distance will be the same, and it will also be exactly equal to the wavelength of the sound wave. Okay, now to move the dialogue or the understanding along a little further, we're going to talk a little bit about the interference of waves as they travel through the rope or through a string. This will be particularly important with string instruments, but the general idea of wave interference is that it occurs when there are two or more waves that interact with each other because they occur in the same place and at the same time. And generally speaking, if I have two waves that are coming towards each other, the way we understand what's happening is by the superposition principle, which says that the displacement due to the interference is determined by adding the disturbances produced by each wave. So, for example, we might have a condition where there's a wave with a crest that arrives from another wave, particularly if you think of this in terms of the surface of the water, and the peak of one wave coincides with the crest of the trough of the other, then those two will add to zero. And that's the additive principle, or superposition. If, on the other hand, I have a wave from the left and a wave from the right, and they arrive together when they both have at the crest of each of their individual waves, then the amplitude of the wave will double. And so, depending on whether the two waves add constructively to get twice as big of amplitude or big wave, or they add destructively to cancel each other out, I can get two different effects. So that's the basic idea. One way we draw this out here is in pictorial form is that if I have a sine wave that from one wave that looks something like this, and at the same time, instant of time, a second wave arrives at the same location as the first wave, then the reinforcement of the waves will double, and we'll get twice as much amplitude. That is to say, the wave will have twice the height of the previous wave. In the case of them arriving when they are out of phase, or when the crest of one wave arrives at the point in space where I have the trough of the other wave, the two waves will cancel each other out, and I will get the effect of zero amplitude or a flat surface on the water. So destructive interference occurs when the crest of one wave overlaps the trough of another. The highs parts of one wave simply fills in the low part of the other, so their individual effects are canceled. Okay. Now we have one example here of two rods that are penetrating into the surface of water. They're going in and out. They are in phase with each other. They are going up and down at a fixed frequency, for example, 1 hertz, and they each generate a spherical pattern of waves expanding out, like the pebble dropping on the surface of the water. But because of interference effects, they may actually arrive at places in between where, for example, if I consider the high blue regions to be the regions where the surface of the water has a maximum high crest, and the dark region to be the region of the water that has a trough, then you can see that there will be interference effects where between the troughs and the crests, the two come together, and they may cancel each other out, which would be the light blue area that I'm pointing to right here. Or they might add coherently together, and their phases and their amplitudes would double, which is not quite so clear, but still you can see that the effect of the two circular patterns is to give a new pattern, which depends on whether these waves add together and double their amplitude at a given point in space and a given time, or whether they are not in phase, or they cancel each other out because they arrive when the crest of one arrives with the crest of the other. So we can do a similar type of experiment with standing waves on a rope that we're tied to a wall. And in this case, we consider the effect of the rope being fixed at both ends. Now, initially, the girl at the end of the string has to be shaking the rope in order to get it to move at all. So we have to start the wave motion. But after the wave is started, then she holds her hand and the rope at a steady point so that where I'm pointing to, it does not move. And similarly, on the wall end, it does not move as well. So if we tie a rope to the wall and shake the free end up and down, we produce a train of waves in the rope. The wall is too rigid to shake, so the waves are reflected back. So I produce a short spike or a brief jerk of the rope. I send a pulse or the sine wave towards the wall, and when it reaches the end of the wall, the reflected wave will in fact be out of phase, and it will cancel because we know that at the end of the rope they have to cancel because there is no way for the end of that rope to move, so the amplitude is always 0, and the reflected wave will be out of phase with the incident wave. Okay, so by shaking the rope at just the right frequency, we can cause the incident and reflected waves to form what's called a standing wave. And basically what this means is that there are certain magic frequencies at which we can shake the rope such that I can get a pattern that changes with time. And so to understand this figure at the bottom, we consider the fact that the wave that there's always one wave traveling to the right and one wave traveling to the left. And when they add together, you can, at different times, you'll have different amplitudes of the oscillation of the rope. So, for example, at one particular time, if where I'm pointing you do have the smallest amplitude wave, at a little bit later point in time, the wave is a little bit higher, and at a third point in time, it becomes the highest again. And then it begins to diminish and go back down until it begins to have a negative amplitude on the left half of the rope and a positive amplitude on the right half, and the amplitude begins to get big. But there are 3 points where the rope never moves. The ends that are being held at, and there's 1 point in the middle. Now this can only happen with what we call a certain frequency that is applied to the rope. We don't always get that for any frequency, but when we do have that happen, we call the incident reflected waves form what's called a standing wave. And the reason it's called standing is because you don't really see the motion of two waves moving. It's not like this full sine wave of the rope is propagating downward. Rather, we see 1 point in the middle that never moves at all, and the points at this distance and this distance are doing their oscillation. So it looks like a standing wave because you don't see the motion of the waves that are reflecting back and forth from both ends. They're doing something like this. Their fingers are, their waves are bouncing off the walls and coming back in. They cross each other and bounce back. And the net result is that we see this standing wave pattern. Standing waves are created by two waves traveling in opposite directions along the rope. We've already said that. The rope is fixed at both ends. The up and down motion in the rope is caused by two traveling waves moving in opposite direction, and each wave gets reflected continuously as it reaches the end of the wall. So what we're seeing here is the addition of two waves moving in opposite directions. If we take the superposition of these waves at a certain time, we get this pattern that you see right here, which is the sinusoidal wave. And at a later time, the deflection of the rope is zero when we add because these two waves now add at a time when they're completely out of phase with each other. That is to say, the trough of one occurs at the same point as the peak or crest of the other one. And then we wait a little bit longer, and now the pattern that you see here in the rope has reversed itself. The positive amplitude has gone negative, the negative amplitude of the rope has gone positive, and so on. And then a little bit later it's flat again, and then it repeats over and over again. So now that we've covered standing waves, I've tried to give you a little bit more of an explanation on how this works. We'll continue on. We're going to see the reason we do this is because this is the exact process that occurs in musical instruments, particularly stringed instruments. And what we're going to see very shortly is that the vibrations of a string on a guitar or a piano or a harp or a violin all have this vibrating structure of what we call standing waves. And they basically have the property that at the ends of the string of the instrument, when you pluck the string or you bow the string with your bow or however you disturb it, you create these traveling waves that go down in either direction to the right or left, and they add together to make this pattern that you see here. This is one example of a standing wave with one node in the middle. The node is the place where we have zero motion of the rope or the string at all times. If we imagine a rope or a tube that is being shaken up and down, that there will be certain frequencies that we can shake the rope that will produce the standing waves. And one of the wavelengths that we can, if you shake the tube at one of those frequencies, you will get a standing wave that looks very much like what we call the skip rope. In other words, the children on the playground playing circle this half wavelength over and over, and in this case the rope is basically making a contour from maximum to minimum amplitude in the middle between the ends, but but only there do you get the maximum amplitude. If you shake the tube with twice the frequency, a standing wave will have half that wavelength, and that would be case B right here, where at a higher frequency you begin to make a wave of shorter wavelength, and that one has half the wavelength, and that will produce the standing wave that we saw in the last slide, which is right here, where you see the oscillations. The oscillations of the rope go up and down at the 1/4 point and at the 3/4 length of the rope, but not in the middle. And then if you shake it a little bit faster again, then you begin to create another standing wave, one in which you have maximum amplitudes at 1/4, 1/2, and 3/4. And if you shake the tube with 3 times the frequency, well, that was the one I just described. And another general property that we've talked about before is that the frequency of the oscillation times the wavelength is always equal to the speed of the wave. But in this case, the wave is the speed of the wave on the rope itself. So it's these 2 waves that are continuously going to each end, turning around and coming back, and they are constantly overlapping with each other to create these standing waves. And notice that you can have the wavelength 2L, wavelength equal to L, or wavelength equal to 2L over 3. Notice that in general, I could have said this is 2L divided by 1, this is 2L divided by 2, and this is 2L divided by 3. The next standing wave will be 2L divided by 4. So in this way, depending on how fast I make this rope oscillate, I can always find standing waves with higher frequencies, therefore shorter wavelengths, and therefore nodes that are closer together. Now, as we've said before, what we're trying to do here is to show you that sound waves can be produced by a vibrating string. We've mentioned some examples of those before. We also get sound waves blown through a trumpet, and they use slightly different phenomena, but we will look at how those devices generate music when we look at chapter 21. Now, in addition to the standing waves that can produce these reflecting waves from the ends of the rope that can produce the standing waves, there is also another wave-like effect, which is called the Doppler shift, or the Doppler effect. Okay, so in the final part of this lecture, we're going to talk about 2 phenomena. One of them is called the Doppler effect, and the other one is related to the what we call the supersonic boom, or the supersonic shock wave. So in the first one right here, we're talking about is the Doppler effect. And basically what the Doppler effect tells us is that if we have a source of sound that is moving towards us, the pitch of the frequency of the sound will increase. If we are standing next to a source that's moving away from us, the frequency of the sound will decrease. And where ears experience that very well, we usually call that quality a pitch referring to the frequency of the sound, whether it's a high pitch or low pitch, means it's high frequency or low frequency. So imagine here that we have a source of sound that is not moving with respect to us at all. And as I activate that sound at a given frequency, and remember frequency is the compressions of the sound wave as the wave propagates through air, there will be, if it's produced from a central point, there will be spherical waves that are expanding. And the arrows indicate that the compressions of the wave, which are indicated by the blue circles, are expanding away from the source, and they will of course travel at the speed of sound, which we will come to very, very shortly here. And furthermore, that the frequency will be the same in all directions. Now, the frequency is the rate, if I'm standing at a given point where my arrow is to the right of the concentric circles, then the frequency is the rate at which these compressions are reaching my ear. So if I have 400 compressions per second that are reaching my eardrum, I would say that sound wave had a frequency of 400 hertz. So hertz is the rate at which I hear the rate at which the compressions are arriving onto my ear. And so in this case, they'll be the same everywhere. Now imagine that instead that the source of the sound is moving to the right while the sound is being produced. In that case, what will happen is that the compressions will be closer together, and the observer here will experience more compressions per second because they're more closely spaced. That is to say, their wavelength, the distance between compressions, is smaller, and he will experience that as a higher pitch sound. On the other hand, if the observer is standing over to the left of the rings, and the train with a whistle is moving to the right, then the time between these compressions will be longer because the train is moving away from the observer. So the basic thread or idea here is that the compressions are further apart and they have a longer wavelength, and therefore they have a lower frequency as the source of the sound is moving to the right. So on one side, we get a higher pitch from the train or the object moving towards us. In the other case, when we're behind it, then we hear a lower pitch relative to the case where the train is not moving at all. So this effect then is the Doppler effect, and it has been observed very much in many applications of audio signals. So then next we're going to talk about the shock wave, a shock wave. The shock wave is one that is produced when the source of the wave, in this case we have a bug swimming on the surface of water, and as he is crawling along the surface, he's making disturbances in the wave. And instead of making concentric circles, which would happen if he was standing still on the water, he begins to make waves that are as he is moving. And as a result, the center of the wave that was made when the bug was located in the center of this second circle that I'm drawing, or the third from the smallest out here, when that disturbance was made, we get the crest of the outer circle. When he's moved a little bit further, we get the crest of the second circle, and when he's moved a little bit further, we get the crest of the third circle. And at some point, if he is moving at the same speed of the wave, which is sort of what we see here, then all of these compressions or disturbances on the surface of the water begin to add up, and I make what's called a wake field. And the wake field is what you see on the back of a motorboat. So in a motorboat, if the motorboat begins to travel faster than the speed of the wave, which it usually and often does, you will get a V-shaped pattern of the waves coming off the tail end of the boat. This is occurring because all the preceding waves that were made by the boat in a preceding way begin to all meet together at this crest and form what we call a super wave. And a super wave will have a very large amplitude compared to the others. Don't need to move. Okay. So this is exactly what happens. So with supersonic aircraft flying faster than the speed of sound, we have the case where instead of the bug, we now imagine that in fact, what's happening is that there's an aircraft, and the aircraft is making disturbances in the air by virtue of its motion through the air, and those disturbances will send out spherical waves. As the aircraft begins to go faster than the rate at which these circles are expanding, then it is leading out in front of those waves, and there's a constructive interference or a superposition of the crests of all the waves at a fixed angle that depends on the speed of the aircraft. So this aircraft now has a speed that is traveling faster than the rate of expansion of these circles. V-shape are formed from overlapping waves when object travels faster than the wave speed. An increase in the speed of the object will produce a narrower V-shape of overlapping waves. So what this is telling us is that as the aircraft goes faster and faster, the angle of this V becomes smaller and smaller, or what we call a narrower V-shape of overlapping patterns. And anyone that has been in the path of or in the path of a shock wave, or has experienced an aircraft, which is usually a military aircraft, going faster than the speed of sound, which is approximately 750 miles per hour, then you will hear a very loud boom that is almost ear-deafening in sound. And for that reason, supersonic flights are not allowed over the continental U.S. Because of the fact that it creates a very large sound disturbance on the ground. So this is the idea of the supersonic shock wave. It's a wave that's formed by all of the crests of the previous waves that are generated along the path of the aircraft, adding together only at a very narrow angular region where the dotted lines occur to produce what we would call a super compression of the air molecules, and therefore a super loud explosion, or a sound very similar to exploding. And as we would view this region of super compressed air traveling over the ground, we would see that it not only is it V-shaped, but if for a person standing at a given location, then one will see that as the jet moves forward, eventually so will the cone, and when this angular V shape crosses the path of the observer on the ground, that's when you'll hear a very loud boom. For a similar reason, you will only hear the boom after the aircraft has passed overhead. You cannot hear the sonic boom when the aircraft is in front of you before it has arrived to you. And this basically shows us that there are actually two cones of pressure that are different from the atmosphere. One is the high pressure cone generated at the bow, and that's the one we've been talking about. But there's also a low pressure cone that follows at the tail of the aircraft. And it's this change in pressure, this abrupt change in pressure, that causes this loud sound in our ear to experience something that's very, 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 very noisy. And it is not required that the source is generating any sound. This is purely the sound due to the compression of air of the jet against the front of the jet as it penetrates through the air. The air acts like a fluid. It acts like a water bath. It makes a disturbance like the bug or the boat on the surface of a lake. And so because just the nature of the jet compressing the air as it hits the static air generates this enormous sound. And this is just a slide I show to show you that there has only been in our history one commercial airplane that has ever traveled supersonic. It was called the Concorde. It flew between 1976 and 2003 or 2004, something like that, for about 25 years. It had a cruise speed of 1,350 miles per hour, and it could fly from New York to London in 3 to 3.5 hours. Very impressive indeed. In order to have that much speed, however, the air resistance has to be very, very small, and so the seating arrangement is very tight, as you can see from how narrow this whole plane was. It could only fit 100 passengers for this overseas flight. And at the time of its last booking, it was about $8,000 for a one-way trip from New York to London. However, it did come with a lobster dinner, so that paid for some of the cost. Okay, so with there, we'll stop. We'll get ready for our next chapter. This is the end of chapter 19. You should be ready to do the homework and begin doing the homework and getting ready for the next chapter as we proceed. Thank you very much.